So the second set of data are the high-resolution watershed inputs. These are the ones that come from Landsat. California is both fantastic and problematic in that it has the greatest availability of cloud-free Landsat dates. Cloud-free is very important. It has some really noticeable increases that we can kind of go after and trying to classify. Things like changes in urban cover and golf courses. But it's also extraordinarily challenging to classify because of diverse topography and climate, and things like human impacts. Crop rotation means that agricultural fields are inconsistent. I also note high soil background in there. Soil is really problematic when we're dealing with reflectance data because it has a high reflectance that tends to provide a lot of noise and minimize other types of changes that are going on. This area is also impacted by large fires, particularly the big sewer site. So we have large fires in 85, 99, and 2008, and then other years when there's smaller but still significant fires. So Landsat data are used in this region, and there's a multitude of dates that can be utilized to try and map land cover. But I ended up choosing fall dates because it's the time of year when it's easiest to distinguish between grasslands and shrublands and aglands because the grass has senesced. Summer is problematic along the coast here because, for those of you that live there know, the coastal fog is pretty prevalent throughout the summer, and Landsat passes over at about 9:30, 10 o'clock in the morning when the fog has not burned off yet a lot of the time. So there are 4 dates that I have processed. There's additional dates available in 05 and 2010, and pretty much every year in the 2000s if there's a particular year of interest for the sampling study, I suppose. The indices that I produced, you're probably familiar with the Normalized Differential Vegetation Index. As I mentioned, we have a soil problem. And so in places where you have high soil background, we use a Soil Adjusted Vegetation Index. That's that SAVI index. NBR is the normalized burn ratio. We use it to identify disturbance like fires. NDWI is the Normalized Difference Water Index. Good index for identifying sort of boggy wetland areas or fields that are flooded. And then TC is the tasseled cap, and it's the greenness, brightness, and wetness corners of the cap. So commonly used for land cover classifications. I utilized historic aerial photos and higher resolution imagery to identify fairly homogeneous sites where I was entirely sure of what the cover was. And I produced 220 data points across a series of classes for the classification. I also digitized some polygons in completely independent areas to use as validation pixels. So I have 2 independent data sets for classification and validation. I used a classification tree random forest approach. Classification tree is sort of the newest, greatest thing. It's an iterative learning algorithm, and it allows the user to interact with the algorithm to see if it makes sense. So things like agricultural fields only occurring on low to no slope. You wouldn't usually find an agricultural field on a steep slope. So we can sort of check those things in the algorithm. And the random forest is basically a series of classification trees. So the forest is multiple trees using a random sample of the training points for each different tree, and then you use a probability map, or that it produces a probability map. Each pixel is the highest frequency of the land cover that was predicted from the forest. So the input variables to this were the 6 reflectance bands of Landsat, the 7 indices that I produced, and initially 3 topographic variables: elevation, slope, and aspect. I ended up throwing out elevation because the model was overfitting using elevation, and it was making a lot of mistakes by overfitting. So there were 15 variables for input. Again, some of the noticeable changes, things like out towards Carmel, 17-mile drive area. Boy, there's a lot more golf courses in 2008 on the right than there were in 1984 on the left. So this is a 25-year change in the frequency and cover of golf courses, which, because of the amount of fertilizer and water used, show a bright green. Another couple of noticeable changes, city of Salinas in the northeastern corner, shown by these two red circles. Fair amount of urban expansion in the city. In the lower left corner and the southwest corner, you can see the change between a fire that had just burned in 1984 to, on the lower right here, there's the regrowth in that area after that fire. I think it's also a good time to point out that that dark red in this false color image of that fire is the exact same dark red that many of those fallow fields are shaded, because of course they were recently burned by the farmer. So it makes it a challenge to try and distinguish between those two classes. So what I did end up trying to distinguish was a water class, an urban or impervious class, an agricultural or golf course class, a forest or dense vegetation class, a more open vegetation, shrubland oak woodlands class, a class comprised of fallow agricultural fields, and I had a hard time distinguishing between unburned and burned, a class of recent disturbance, particularly fires, and then the eighth class was sort of the senesced grasslands with a high soil background, and in some cases it was simply bare soil with a few tufts of grass here and there. So those ended up in the same class. So the classification itself, with a lot of tweaking, still had some problems confusing things like senesced grasslands with fallow fields, particularly in places where there are hay fields all over the place, where the farmer goes out and mows the hay and it looks just the same as a grassland. The only way that I can tell the difference is by the shape of the field, but this algorithm doesn't take into account shape. Things like forest versus shrubland, it's really, really difficult in this region to disaggregate those two. There's also a shadow problem because forests in some of those deep canyons out in the Big Sur, they have enough shadowing that it almost looks like the same as water because it's just dark. Burned fields, of course, looks just like wildfires. In the validation between the training sites and the validation sites, the areas that I just mentioned, you can see where there's quite a bit of confusion. So in this, the validation sites is in the columns, and the class or the rows are the mapped values for that. On the very left is the Kappa index agreement for each class, and this is for the truth. The values are actually in the wrong spot, but it just made a lot of sense to show it this way. So for each class, this is how well that class got mapped. So the biggest problems were things like vegetation getting confused, classes 4 and 5, and then to some extent the agricultural and or the fallow agriculture and the recent disturbance. Particularly if you look at like class 7, reading down the column, well over half the pixels in class, or I'm sorry, about a third of the pixels in class 7 ended up getting classified as fallow agriculture. So just an update on sort of the progress. So all of the Landsat data for California are processed and the indices are produced and the classifications are complete for 1984 and 2008. Still working on classifications for the other dates, but I'm sort of wrestling with this accuracy problem at this point. All of the MODIS LAI data are processed for California, and they're loaded into a time series analyst in the Adresi Earth Trends Modeler, and ready for processing. And then all of the MODIS land cover data are processed for California and ready for change analysis. Some of the MODIS data are processed for Alaska. The Katmai region, I believe, was the next highest priority. And I'm looking into the accuracy of the snow products in that region. And the snow products are Dave Selkowitz, for those of you who know him up at Alaska Science Center, he's pretty confident of snow product accuracy for Alaska. I'm not so sure about Pacific Northwest, but that's what I'm looking into. So some of the data production decisions that need to be made are related to, I guess, what all of you really want to put into the model. Because there are a lot of different types of variables that I can produce. Things like linear data for a given site, or one, a linear data set for each site that looks at temporal change, spatial changes, or singular static pieces of information. We need to talk again about the watershed boundaries, because those boundaries will inform sort of these spatial assessments like I showed with the leaf area index. What's the polygon over which we're going to produce this linear change line? And there's potential to do a couple or three per site if you want to look at different potential watershed sizes. And then what are the proxies that are actually going to be useful? Because I can come up with a lot of different variables, but it doesn't mean that they're actually going to be useful to the model, especially given the limitations of the data, like the land cover accuracy issue. And then length of change. For every site, does it make sense to look at 1984 through 2010? When there's not annual resolution for that data set. So that's a sort of a question for all of you.